In this video, we will discuss how to solve questions dealing with partial pressures and with collection of gas over water. So there is this law, and it's called Dalton's laws of partial pressures. And what it says is that your total pressure, let's say you have a total pressure of 752 millimeters of mercury. It's going to be, that total pressure is going to be equal to the pressures of each individual gas. And so, for example, here, if I can take some oxygen gas and I combine it with some nitrogen gas, if oxygen is 159 millimeters of mercury, then I would also be able to know what's the pressure. So that was the pressure of oxygen. I would know the pressure of nitrogen, which is down here as 593 millimeters of mercury. And if I combine those in the same container, they will give me this overall pressure of 752 millimeters of mercury. Now, this is very common. Some people like to overthink this. There's just not much to it. It's just that all the gases add up to be the total pressure. And something that is new is calculating mole fraction. And so mole fraction is given the symbol of like an italicized little x. And all it is it's what percent of all your moles are a specific chemical. So you take your moles of gas 1 divided by your total moles, and that would give you the mole fraction. And so let's say I had 5 moles total, and only 3 moles were oxygen. So my mole fraction of oxygen would be 0.6, meaning, here's what this means, and this is where mole fraction is why it's used, that 60% of moles, and I should say gas moles since we are in the gas unit, 60% of gas moles are oxygen. And what that also means is 60% of the pressure is from oxygen. Okay, so what I have in example problem number 1 here is that we've got a total pressure of 10 atmospheres, 10 ATMs. We've got 4 grams of helium gas, and we've got 32 grams of oxygen gas, and I have forgotten to write it here, but I want to know what is the pressure of each gas. Okay, so the total pressure, which is given, is going to be equal to the pressure of helium plus the pressure of oxygen. So pretty much if I can find this guy or this guy, I will be able to find the other one. And so a good rule of thumb in chemistry is figure out the moles. So I'm going to take 4.00 grams of helium and 32.00 grams of oxygen. There's 32.00 grams of O2 and 1 mole of O2, so I have 1 mole of oxygen gas. And there's actually 4.00 grams of helium and 1 mole of helium, and so I actually have 1 mole of He. And so I'm not given any other information. Later in the unit, we will talk about how if you know moles of a gas, you can actually just convert it to the pressure using something called the ideal gas law, but we haven't talked about that yet. So here's what I know, is that the mole fraction of helium is 1 mole of helium divided by 2 moles total. So that is 0.5, meaning that 50% of the gas moles are helium and 50% of the pressure is because of helium. So what I know is that my total pressure is 10. Well, 50% of that, or 5 ATMs, must be because of helium. And if I went through and I solved this out for the mole fraction of O2, that this will be 5 ATMs as well. In this first example problem, the numbers are nice and neat, okay, but they're not typically this nice. Okay, now vapor pressure. Vapor pressure is the pressure of a substance above its liquid phase typically. It could be solid phase, but we'll just say above its liquid phase because that's what we'll be dealing with in this unit. And so let's say I have some water here. So there's some water, there's a water level, and this is at low temperatures, and so the particles have some low kinetic energy, but some of them have enough energy they do make it into the gas phase. If I want more of them to make it into the gas phase, I could just raise the temperature, and the particles have more kinetic energy now, and so what we have just proved is that more of them will be able to get into the vapor phase, so higher temperature equals higher vapor pressure. And this will become important when we collect gas over water. So in lab, if we want to study gases, we have to be able to trap them somehow because gases expand to fill their container. And so I don't want the container to be my classroom or even anything larger because that's just too large for me to deal with. So what we will typically do is we'll have an Erlenmeyer flask. We'll have some sort of reaction going on where we're getting a gas. And then we will use tubing to have the gas travel through the tube. And then what we'll do is we'll have another tube where we collect the gas. And what we'll do to keep the gas from escaping is we will basically submerge the tube first in water, and then the gas will come into the tube and displace the water. And so there's a little bit of water in there, and you'll get really good at this once we do it in lab. Now the problem with that is that when we collect gas using water displacement, we've got, for example, here we've produced some hydrogen gas, but because there's liquid water here and water will have a certain vapor pressure, we also have some water molecules that are contributing to my pressure, and I don't care about the water molecules. And so what I would have to do is that if I measure this pressure, let's say the pressure inside of there was 5 atms. Well, 1, 2, 3 waters divided by 1, 2, 3, 4, 5, 6, 7, 8, 9 total. We have 1/3 of that pressure being water. So I would have to subtract away 1/3 of this. Okay, the formula for this that we're going to see oftentimes is that if I know the total pressure, P total, or P ATM, typically pressures are given in ATM. And this is the gas that I care about. We can subtract away the pressure of the water, which we can just get, and I'm going to show you. This is just from a table, and we'll show how to read that here in a minute. But this is from a table. Okay, if I subtract away the pressure of the gas, I will be able to get whatever that number is, and that would be useful, this pressure of the gas. Okay, so let's see what this looks like. In this first example problem, we have oxygen that is formed. This is the only gas that's formed in this reaction. And this is the decomposition of potassium chlorate. If you remember earlier in the year when we did decomposition with a gummy bear, that was this reaction. And the total pressure during the experiment was 731 torr, and we're at 20 degrees Celsius. And I want to know just the pressure of the oxygen being collected. So partial pressure, it sounds fancy, that just means the pressure of oxygen being collected. Well, the total pressure was 731.0 torr, and we had the pressure of oxygen, that's P gas, and then because I collected it by water displacement, I also have some water vapor in there that I don't really care about. So what I have to do is I just have to figure out that at 20 degrees Celsius, how much is the water vapor going to contribute to my pressure. So I'm just going to look up at my table, and we have our millimeters of mercury column, which that is the same as torr. We're at 20 degrees Celsius, so that is 17.5 torr. And if I subtract away 17.5 from each side, my pressure of oxygen will be 713.5 torr. Okay. What we could also do is say, in number 3 here, we've got some helium gas. We collect 723.4 milliliters. We collect it over water, so that means we have water displacement and that there is some water vapor in my gas that I don't care about. 80 degrees Celsius, and the total pressure is 845.1 millimeters of mercury, and we want to know just the pressure of just the helium. So P total equals P gas plus PH2O. The total pressure is 845.1 millimeters of mercury. The pressure of the gas that we care about is helium. And then I've just got to figure out my water vapor pressure. Well, we're at 80 degrees Celsius, so I'm just going to scroll up and say, okay, at 80 degrees Celsius, the millimeters of mercury would be 351 or 355.1. So if I subtract that away from each side, the pressure of helium that I get is 490.0 millimeters of mercury. Okay.